Okay, let's consider another example. We are going to consider the case when f of z is equal to sine z, and we are going to find the Maclaurin series for this function. That is when z0 in this expression is equal to 0. So what we need to do is to find the derivatives, the nth derivatives of the function sine at the point 0 for any value of n. It turns out that when n is even values, n is an even value, then we have that this term vanishes. Let's just confirm this. We know that the derivative of sine is equal to cosine. The second derivative is then equal to minus sine, and the third derivative is equal to minus cosine, and the fourth derivative is equal to sine, which is just equal to f of z. So we now can do the same procedure one more time. The fifth derivative is just equal to the first derivative, and so on. So what does this mean? Well, we are going to insert the value z0 equal to 0 into these expressions, and then we obtain that the first derivative at 0 is equal to 1. We have that the function itself at 0 is equal to 0, of course. The second derivative of the function at 0 is equal to 0, because minus sine of 0 is equal to 0. And the third derivative is of course equal to minus 1, because cosine of 0 is equal to 1. And finally we have that the fourth derivative at the point 0 is equal to 0 by using this expression. So we can continue this infinitely many times, and we easily obtain the same sequence: 1, 0, minus 1, 0, 1, 0, minus 1, 0, and so on. So what does this mean? It means that the derivative, if we take the 2nth derivative at 0, then we obtain 0. You see that for all even values, the derivative, the second derivative, for example, the fourth derivative, the sixth derivative, etc., is equal to 0. For odd numbers, here we obtain that it's either 1 or minus 1. So the derivative of 2n plus 1 at the point 0 is either minus 1 or 1. And we see that we can use this formula. Just check it out. If we put n equal to 0 here, we obtain the first derivative at point 0, which is equal to 1. We know that. And minus 1 in 0 is also equal to 1. Let's check for this value. The third derivative, that means that n should be equal to 1. Then we get 2 times 1 plus 1 is equal to 3, and n is equal to 1, so we have minus 1 in the power of 1, which is equal to minus 1, which is exactly what we have here. So we see that this formula is valid, and this formula is valid. This means that we can do as follows. We know that the general formula for the Taylor series is like this, and we can avoid all even numbers here. The even derivatives of the function f at point 0 is equal to 0. So we only need to take care of the odd derivatives of the function. So then we obtain this expression. Sorry for here we should have faculty. Sorry for this. You see that it's n faculty here. And we are multiplying this with z in the power of 2n plus 1. And the counting variable n is not the same as the counting variable here, but we see that this will be the correct value, the correct expression for the series. So we have this expression, and we know that the odd derivative at point 0 is equal to -1 in this counting variable n. So therefore we can replace this by this. Here you see we have got the faculty sign back. So this is the formula for the Taylor series in the case when the function is equal to sine.